Actually, before I jump in, for people who are attending online, I just want to confirm, so please let me know. Can people attending online hear me?
Yes, sir, I can.
Okay. It's kind of weird. When I joined the meeting, it had myself muted, and then it took a long time to unmute. Okay. I don't know if there's anyone up in the Hattiesburg classroom looking to connect. Apparently not. So, okay. So, and if we're getting down, not too far from the end of the semester, I hope to make one more appearance here, presumably sometime in November. Maybe like a week before Thanksgiving or something like that. Okay. So last time what we saw was how to approximate derivatives using Taylor expansion to come up with approximate differentiation rules or finite difference formulas. And now we're going to look at alternative approach, Lagrange interpolation. So one difference with one key difference between the two in terms of practicality is that with the Taylor expansion approach, you set up a system of linear equations to solve for the coefficients in your finite difference formula, and that's a full matrix. Most of the entries will be non-zero. Here, there's no need to solve a system of equations at all. So the idea is that if we're approximating f of x by its interpolating polynomial in Lagrange form, or we've selected certain x values, xj, as interpolation points, then what we can do is really the approximation of a derivative is the derivative of the approximation. And what I mean by that is to approximate f prime at x naught, we'll take this Lagrange polynomial and take its derivative and evaluate it at x naught. And since in this Lagrange interpolating polynomial, the f of xj, those are constants. The only part that depends on x is the Lagrange polynomial. So really we're taking the derivatives of just the Lagrange polynomials and evaluating them at x naught. So what we get here is f prime of x naught is approximated by a linear combination of these values of f at our chosen points, and the derivatives of the Lagrange polynomials at x naught are the coefficients in that linear combination. And I mentioned here one way to obtain the Lagrange polynomials if you're working in MATLAB, and you can use MATLAB's function for polynomial interpolation, polyfit. So you can specify that for a given Lagrange polynomial, one of the y values is equal to 1 and all the rest are equal to 0. And that gives you the coefficients of the Lagrange polynomial. Once you have those coefficients, you can use MATLAB's function polydir that computes the derivatives, or computes the coefficients of a derivative of a given polynomial. And then once you have that, you can evaluate that polynomial at x naught using polyval. So that's one way to get an approximate derivative, and that would give you these coefficients. Now, generally, these kind of approximate differentiation techniques rely on equally spaced points. And the reason for that is in many applications, you're not normally taking a derivative at just one point. You want a derivative at lots of points. This is very common, for instance, in methods for solving numerically solving differential equations. And if your points are equally spaced, then you can construct just one finite difference formula and use that for all the points. Whereas if they're not equally spaced, you have to come up with different rules for each point. It's much more of a pain. So if your points at which you're evaluating f to approximate your derivative are equally spaced, then things simplify a little bit. So, because what you can do is make a change of variable. U equals x minus x naught over h. Now, what this change of variable does is it takes your points at which you want to evaluate f and maps them to the integers that are just the indices of these points. So from minus j up to k. And just like last time, we have negative and positive indices corresponding to points that are located either to the left or to the right of x naught. So now all you need to do is get the Lagrange polynomials not for these points, but for these integers. And then you just have to remember to divide the coefficients by your spacing h. And that's because of this formula. The change of variable, if you notice, we have a scaling factor of 1 over h, so we have to include that. So here's an example, and we actually came up with this finite difference formula last time using Taylor expansion, but now I'll show you how to get the same rule using Lagrange polynomials. So we want to approximate the derivative using values of f at these 3 points, x naught plus h, x naught plus 2h. So we look at the multiples of h that are included here, 0, 1, 2. Those are the points that we use in constructing the Lagrange polynomials. So what you can do is, hold on a second. Oh, okay. Okay, apparently there's a problem with the meeting code. Let me check on that real quick. Okay. All right, so the technical difficulties up in Hattiesburg. Okay. Yeah, sorry, I see the code that I had emailed previously. I apologize. I don't know what happened there. That it was a different meeting code than what I just sent this time. So if you want to, you can, and you know you're able to attend a meeting a different way. But if that can work, then great. Sorry about that. Okay. All right. Now, so what we have here, this is the first Lagrange polynomial that's equal to 1 at 0, and it's equal to 0 at the other points, 1 and 2. And here I've just written it out simplified, just so it's easier to see what the derivative is. So we go ahead and take the derivative. Okay, we get x minus 3 halves. But then we evaluate this at 0, and that's our coefficient. Oh, okay, apparently we do have Hattiesburg on the line.
Yes.
Okay. Great.
There we go. Yay.
Thank you.
Oh, good class.
Okay. Then for a second Lagrange polynomial, that's equal to 1 at 1, and it's equal to 0 at the other points, 0 and 2. So we have that here. Again, take its derivative, plug in x equals 0. That's our coefficient for a second point. And then we do the same for the third point. Lagrange polynomial is equal to 1 at 2, and then equal to 0 at 0 and 1. Take a derivative, plug in 0. So now, so now f prime and x naught. Okay. So we take our coefficients, so we have minus 3/2 times f of x naught plus 2 f of x naught plus h minus 1/2 f of x naught plus 2h. Now, since we have these fractions in the denominator, that's going to rewrite this with a 2h down below. So we have minus 3, plus 4, minus, okay. All right. Okay. Using these coefficients. So the coefficients are just derivatives of Lagrange polynomials for these integers evaluated at, their derivatives evaluated at 0. And these turn out to give the same finite difference formulas as Taylor expansion, just because both the Taylor expansion approach and Lagrange interpolation approach rely on polynomial approximation of f of x. Okay. The questions about how Lagrange polynomials were used to obtain this formula.
The derivative is always done at x naught.
Yes. Yeah. Yeah. So you want a derivative at a certain point, and then other points you're using here are described relative to that point. There's some spacing, it's a multiple of h away. So more generally, to use any number of points, still assuming, actually right here, this formula here actually does not require equal spacing, just more convenient if it is, that the coefficients are given by the derivatives of Lagrange polynomials at x naught. Now, however many points you have to the left and right, so j plus k is the degree of all the Lagrange polynomials that you will be using. So as an example, the example here, j was 0 because we didn't have any points to the left of x naught. And then k was equal to 2. So the degree of Lagrange polynomials were all 2, these quadratics here. Okay. Now it turns out that Lagrange interpolation can also be helpful for getting an error formula. Because what are we doing here? This right here is a derivative at x naught of the interpolation error, because the interpolation error is f of x minus Pn of x, where Pn is the Lagrange interpolating polynomial at degree n. I need to make clear here the value n here. That's, as I mentioned, that's a degree of the interpolating polynomial. That's just given by j plus k. So we're taking an interpolation error, which is what we have here in the square bracket. So this is from that theorem in section 7.4 about the interpolation error. And we're taking the derivative of this whole expression with respect to x. And then here, the vertical bar, this notation means that it's evaluation. So we're taking this whole derivative and then we're evaluating it at x naught. Now, the thing is, we have here an interpolation error. This is an unknown point, c of x. So how can we possibly take the derivative of this if we don't even know what this is? It turns out not to be a problem in this case, but only because we are evaluating this whole expression at x naught. Because if you were to take a derivative of this whole mess, you'd have to use a product rule. So you'd have to take this times the derivative of this plus this times the derivative of this. So in the term that involves a derivative of this, that's going to be multiplied by this expression that's not differentiated. But then you plug in x equal x naught in here. One of these factors is x minus x naught. So this would become 0. So the portion of a product rule that comes from differentiating this ends up not being included. So all we're going to have is this part as is, you see that over here, with x equal x naught. This is still an unknown point though. And then the derivative of this evaluated at x naught. But what that turns out to be, also by product rule, is all of these linear factors multiplied together except for x minus x naught. And then you set x equal x naught at the end, because you're evaluating it at that point, and this is what you get. So this is the general error formula arrived at using the polynomial interpolation error. Now here again, we're not assuming equally spaced points. That's not required for this error formula. But as I mentioned, if you do use equally spaced points, that certainly helps, because you can use Lagrange polynomials at the integers. You just have to remember to divide your coefficients by h when you're done. One of the homework problems for this section, so it's exploration 914, involves taking this error formula and simplifying it in the case of equally spaced points. So you can use this in here to simplify this expression somewhat. And since we already have certain example finite difference formulas that were given in the text, and I covered some of them on Tuesday and showed you their error terms, when you work out this problem here and you get your formula, you can check it against some of those examples and make sure that your expression is correct. And this is the order of accuracy, generally speaking, order h to the n, where n is j plus k. Although, as we saw last time, sometimes the order could be a little higher because of error terms canceling. That's something that can happen. Okay. Questions at this point? I need to make a quick comment about higher order derivatives. So what you can do there, it's not difficult to extend this in terms of getting the approximation. Derivatives, I can't type, of Lagrange polynomials. x naught. So, as an example, f double prime x naught, that would be approximated by sum of your f values times the second derivatives of Lagrange polynomials evaluated at x naught, where, as before, n is equal to j plus k. So there's no difficulty in getting finite difference formulas using this approach, but it's more difficult to use this approach to get the error formula, because what happens in this case, suppose it's second derivative, for example, then you need to take the second derivative of this, and this part with the unknown point is going to appear. But there are other, but you can always just rely on Taylor expansion to get an error formula that way, because everything works out the same anyway. Some of the explorations in this section that I did not assign, and which you can be thankful for, explore certain other approaches to getting error formulas in certain cases that involve a lot of trickery. Okay. Okay. Now, so what about sensitivity? And back in chapter 2, I talked about forward error, backward error, and how they're related by the condition number, what it means for a problem to be ill-conditioned or well-conditioned. Oh. Is there a question? I thought I heard something.
Oh.
Okay. So what's going on with numerical differentiation? So we want to get ideas of a condition number, and as discussed in chapter 2, just generally speaking, the condition number is forward error divided by backward error. So what would the forward and backward error be in this case? Well, forward error is just the error of whatever it is you're trying to approximate. So here, this error term, whatever error term you get for your finite difference formula, that's the forward error. So here I'm just using forward difference, just because that's the simplest finite difference rule. And this is the error term that I showed you last time. So now we have a forward error, but now the question is, what is the backward error? And it turns out that in this case, that's something we can get. Because what is backward error? It's based on the assumption that whatever it is you're computing, your approximation is the exact solution of a nearby problem. What is it we're trying to compute? We're trying to compute f prime of x naught. And so we get some approximation. Well, we already know that our computed value, our approximation to f prime of x naught, is the exact solution of a nearby problem. Because what are we doing? We're approximating f of x by a polynomial that interpolates f at the selected points. And then we take the exact derivative of that. So our approximate f prime is the exact value of Pn prime, where Pn is the interpolating polynomial. So, so a distinction between our exact input and our approximate input, that's a backward error. What is our exact input? That's f of x. That's what we're trying to take the derivative of. Our approximate input is the interpolating polynomial, Pn of x. So f minus Pn, that's the backward error. So, if we return to this example of a forward difference, all we're doing here is we're interpolating f at x naught and x naught plus h. We're using a linear interpolating polynomial, P1 of x. So, so now what I do is compute the interpolation error. And, okay. And that's what we have here. Okay, actually, there's something wrong here. This is certainly not equal to this. Okay. Sorry, it's something I wrote a couple of years ago. Okay. What I would like to do, though, is have an upper bound for it. Okay. And it can be shown by taking the derivative of this with respect to x and setting it equal to 0, look for a critical point, that the critical point is going to be halfway between x0 and x0 plus h. So the maximum absolute value of this portion right here turns out to be h squared over 4. And that's what leads to this h squared over 8 factor here. So what I can say is that this is can be bounded by the maximum of f double prime at an unknown point just between okay. Times h squared over 8. So at least here we have a handle on what the interpolation error is like. So here we have an expression for our forward error. Sorry, this is our backward error, and this is our forward error. But notice that both of these involve a second derivative. But in the forward error, we have a factor of h over 2. In the backward error, we have a factor of h squared over 8. But for a condition number, we're dividing forward error by backward error. So we set aside the f double primes that appear in both. What we end up with is a ratio of 4 over h. So that's pretty awful, because h is supposed to be small. So as h gets smaller and smaller, this problem of numerical differentiation gets more and more ill-conditioned. So numerical differentiation in general is a terribly ill-conditioned problem, because generally we're using small values of h. Now, I showed you before how bad things can get, where you're using the find a difference formula like this, and as you let h get smaller and smaller, at first the accuracy is improving, and then things get really, really awful. And this sort of thing that happens when you're dealing with such a ill-conditioned problem, that even though this error is going to 0, as h is going to 0, you also have round-off error to consider, and that is not included in this analysis, at least to this error term. So the analysis that leads to this error formula for this finite difference formula or any other is basically assumption of exact arithmetic. But whatever error you have in evaluating f at the various points, those errors may be small, but then you're dividing by h, and that causes those errors to be amplified. And the smaller h gets, the worse that situation is. What you can do is try to balance these considerations. That since this error is decreasing, but round-off error is increasing, try to find a right value of h that leads to the least error overall. But it's only an estimate because you only have a rough idea of what the round-off error can be. But also, such an estimate turns out to be dependent on f. So there's no hard, fast rule that would apply just for all functions. Depends on, because it depends on derivatives of f and so forth. Okay. So that's one thing that's unfortunate, that we have no condition problem. Now, next week I'm going to start covering numerical integration. And as you know, integration is essentially an inverse of differentiation. And so when you have a problem that is ill-conditioned, if you're solving the inverse of that problem, you're trying to go the other way, so the sense of what's input and what's output is reversed, then what's ill-conditioned when going the other direction becomes well-conditioned. So numerical integration is actually a well-conditioned problem, which I'll show you when we get to that. At least here we're these very abstract concepts that I introduced in chapter 2, the forward error, backward error. And for certain problems, we actually can get a handle on these things, and that gives us an idea as to what we're in for in terms of accuracy and robustness, conditioning, so that we're not caught off guard when things go badly. And actually running these things like in MATLAB or whatever. Okay. All right, do we have questions about anything that was covered here?
Can you go back over that last part, the max?
Oh, this right here?
Yeah.
Okay. So all I was doing is just trying to establish an upper bound on this. And this is something similar to something that came up in a recent homework problem. Actually, also one of the problems, a few of the problems on the midterm.
Yeah.
Where, okay, so we had to find upper bound for this, and then separately find upper bound for this. So here, we're just going to say, well, whatever the maximum this is. Now, this unknown point, the only thing we know about it is it lies in the interval containing the interpolation points. But those are x0 and x0 plus h. So that's why I have this.
Okay.
Yeah, is that what you're asking about?
Yeah, that's what I was.
Okay, yeah. Well, since what I really want to do here is divide forward error by backward error, an upper bound is actually not what I need. Anything a lower bound, because then if I want to get an upper bound on the condition number. Now, on the other hand, if h is small, then chances are f double prime is not changing very much on such a small interval. So it's not unreasonable to think of these f double primes as canceling out, because on such a small interval from x0 to x0 plus h, f double prime could very well be nearly constant anyway. But the main thing is what's going on with the powers of h. And because the forward error has a lower power of h than the backward error, and when you divide these, then it's a bad situation.
So h is always your distance, right?
Yeah, your spacing, yeah.
But this, it doesn't matter. It doesn't have to be equally spaced.
Okay, yeah, these formulas here do not require equal spacing.
So your h, what would your h be? Your h would be different for each.
Oh,
So like x0 to x0 plus h could be different than x0. I guess it would. X0 plus 2h might not be your.
Oh, like if you're taking derivative of several points.
Right.
Yeah, so you could have like x0, x1, x2 that could all have different spacings. Here we're just focusing on finding derivative at one point.
Okay.
So like whatever spacing, that's what we have. But yeah, there are a lot of applications where you can't just evaluate f at any point you want.
And it may not exist, right?
Yeah, you may not have that information because maybe you don't have a formula for f at all. And so, like, if you're given a vector of values of f at selected points, equally spaced or not, then you could use a formula like this to approximate derivatives at those points. At least this gives you an idea for filling in the appropriate spacing between whatever 2 points you were looking at, what the error might be. But the h's in this forward and backward error comparison, those are the same.
I think I was just confused because if it's more ideal conditions, the smaller h gets.
Yeah.
You know, you would have more accurate points, I guess, closer and closer points anyway. Estimate the polynomial, right?
Yeah,
Which should be more accurate, I would think.
It is in the sense that, as based on this, it is more accurate in this sense, that this error is going to 0. The condition number is not really so much about accuracy, but rather sensitivity. That a small change in f can lead to a large change in the approximate derivative.
That makes sense.
That's the sort of thing you don't want to have happen, because then it makes your answers hard to trust. Whereas, like with integrals, an integral is area under a curve. We're talking an indefinite integral, and suppose your function f changes at around a point. That's not going to affect the area under the curve very much because it's a local phenomenon. So that's why integration is a lot more stable. But a derivative is all about local behavior. And something changes in f here, and that's why rounding error is a big problem. Anything that happens here gets multiplied by that 1 over h. And that's what makes it so sensitive. And if you could trust, for whatever reason, depend on these values, f of x naught plus h and f of x naught, to be quite accurate, then your derivatives will be accurate as h goes to 0. But can you really count on that? And even if these values individually are exact or very close to exact, you're still subtracting them. You're still incurring cancellation error. And this shows why, how math problems are solved in a non-numerical analysis setting is so different than what happens here, because now all of a sudden you have these things to worry about that didn't even matter before. All right. Other questions, whether on this or homework?
Sure I will when I get to that homework.
Okay. I just realized that I'd forgotten to post this homework. I did post it on Tuesday. Of course, due dates don't really mean anything at this point. If I take a look at I know I have some grading to catch up on, sorry about that, and I will catch up on that soon. Although, considering that there's still 21 people in the class, but I don't have a huge number of assignments to grade, which means their assignments are not coming in. So what it's looking like, and of course I expected this because this is what happens every year. The ton of homework coming in at the end. So, but you know, we all know what we're in for on both sides of it. Okay, the thing to keep in mind is, let's see. Actually, I look at a academic calendar. Just so everybody has an idea of what they're working with. Okay, so I'll just make a note here. Okay. Okay. Because on the 13th, which thankfully is a Monday, not a Friday, this is time, that's when I must put your final grades in SOAR. And I try not to be last minute about that. So that's why I'm setting this, just so so that I have time to grade them. And I've learned from previous years how to optimize that process so that I can get through them quickly, but still fairly. Okay. So let's both try to let's all try to, including me, stay on top of these things. Okay. All right. Questions of any kind?
I think I'm a little confused as to what like a problem of one of these would look like as far as, so these were in generic cases, right, where we don't actually have a point, we don't actually have values, right, so would we just have a set of points and then we're doing Lagrange and then we're doing
okay, so an example of a problem would be given these points, like, you know, x naught plus or minus certain multiples of h, derive the finite difference formula using, you know, either Taylor expansion or Lagrange interpolation. I think one of the homework problems calls for both. And also, what is the error term? Yeah, so it's something like that. For the final, I'll be doing the same thing as for the midterm. It'll be a practice thing.
You happen to know if we'll need, so my computer crashed,
Okay.
my other one, and it had, everything is normally in the cloud except for MATLAB folder, so I forgot to save that to the cloud. So I had homework 4 done and submitted. I think that was like the Lagrange.m files.
Right.
Will we need those? Do you think, like those? I know because I think there was somewhere it was like use your, some of the questions used your previous code a little bit. Okay,
so for one problem for this section that I covered today, does rely on a function called make Lagrange.m.
Okay.
So I just posted it.
I can probably pull it down, I think,
Okay.
from what I submitted to you, if I needed to.
Yeah, I had to change the assignment because I realized that one of the problems I was going to assign, I actually gave the answer away in class on Tuesday, so. It happens. Okay. Anyone out there in virtual land have any questions? We're all like, "Can this end now, please?" One thing I want to check on, see if it's in the syllabus or not. Getting the homeworks. Where'd it go? Oh, not in here. Okay. Okay, so because there are, we're looking at this, all the assignments, we have 9. Okay, there are 10. So this section right here is homework 6. There are 10 assignments altogether that involve explorations, and I'm not talking about the quizzes. So the lowest one of those will be dropped. So, a little bit less pressure. But all that means that no one does number 10, but that's fine too. Okay. Okay, I will end the recording at this point, but anyone who is here or somewhere, if he still have any questions, then I'll stick around for that.